Going to discuss about transformers efficiency. Efficiency by the definition is the ratio of output to the input. If it is transformer, then it is the output of delivered by the transformer to the input supplied to the transformer. Then therefore P, the transformer efficiency, is described as output, and in case of output to the input, and input is output plus loss. In transformer, output is described as V2 I2 cos of theta 2, because the load voltage across the load is V2, the current flowing in the load is I2, and the power factor of the load is cos of theta 2. By the definition, we know P is equal to VI cos theta. Now, this is the output and this is the load, power delivered to the load, and the losses in transformer is described or divided into two parts. One, it is constant loss, another it is variable loss. The constant loss, as the name indicate, whether transformer is having any load or not, these losses takes place. They are also known as core loss, because the core of transformer is made of iron. Sometimes they are also known as iron loss, and hence there are three terminology used for these losses. This is constant loss, core loss, or iron loss. Whereas the second part of the loss is variable loss, and variable loss are due to the resistance of the windings R1 and R2. Because when current is flowing in winding primary winding, the I square R loss takes place. Similarly, when current is flowing the secondary winding, I square R losses takes place. Generally, the winding of transformer is made of copper or aluminium, but in most cases it is of copper, and hence these losses are also known as copper loss. Variable loss, copper loss are same. Now, the constant loss. Constant loss, because we know the constant loss takes place in the transformer core, and they are there even when there is no load. And hence, when, whether transformer is having a load or not, these losses takes place. That is why they are known as constant loss. Now, constant loss occur in a transformer core because of the two reason. One, it is hysteresis, another it is eddy current. Hysteresis here means when AC supply is connected across the transformer winding, there is a development of magnetism, and this magnetism changes because of change in the polarity of the supply. In positive half cycle, if there is north and south, in negative half cycle, the poles are changed from south to north, and hence this reversal of magnetism will causes extra loss, because of the magnetic dipoles will change their direction from north to south or south to north, and hence they are known as hysteresis loss. The another part of the loss is eddy current, because we know transformer core is made of a magnetic material, and a magnetic material is generally a good conductor of electricity, maybe having a different internal resistance. Now, if this core is placed within a coil, the coil is one coil is there, another coil is there. Between these two coils, and EMF develop in these two coils. Some EMF will develop in this core itself, because this core is in itself a complete path, and this complete path, because of this complete path, some current will flow in this circuit, and let this current is eddy current. And because this core is having some resistance, that R is eddy current, resistance of the core, and the losses will become I square R, and hence eddy current loss are nothing. These are the losses due to the current flowing in the core of the transformer because of eddy current. Whereas hysteresis loss are the loss in the transformer core because of reversal of magnetism, and hence these two components occurs in the core of the transformer, and transformer core is made of iron, and sometimes they are also known as iron loss. Now, the variable loss. Variable loss depends upon the resistance of the winding. In primary side, the current is I1, and hence the loss is I square R. In secondary side, the current is I2, the loss is I2 square R. Now, if parameters are referred to the secondary side, then equivalent resistance can be taken. in secondary side current is I2, and hence the total power loss due to the resistance of the winding is I square I2 square R equivalent. Now, considering the efficiency of transformer depending upon the output and output plus losses, these two losses. Now, if we know this efficiency is at 100% load, 100% load means whatever the capacity of transformer is, that is defined as P2, and P2 is equal to V2 I2 cos of theta 2. Here V2 is the total voltage or normal voltage of the transformer at full load. I2 is the total current or normal current at in the transformer at full load, and the power factor of the transformer at full load. Now, if we consider the transformer is subjected to half of the load, then the output will become P2 by 2. Similarly, we know the current PC losses depends upon current I2 square R equivalent. The current will also be half. If current becomes half, then PC will become I2 upon 2 of square R equivalent. Therefore, the PC will be 1/4 of the normal value at half load. If it is at full load, it is at half load. Then PC by 2. PC by 2 is nothing but the losses at half load. And the losses at half load is I square by 2, and hence it will become PC. If earlier the full load loss was PC, at half of the load it will become PC by 4, and therefore we have taken PC by 4. P2 is half of the power, total power P2 by 2, and this is power P2 by 2. Constant loss is independent of the load, whether transformer is subject having a some load or it is not having even a small load, these losses will be constant. Now, similarly, if the load is reduced to 1/3, then power output will become 1/3, whereas the copper loss will become 1/9. Similarly, if the output has reduced to 1/4, then P2 will be P2 by 4, whereas the copper loss will be 1 by 16, and iron loss will remain same, and so in that way, in this way, we can find out the efficiency of transformer at any load, provided we know the full load rating of the transformer and full load copper loss of the transformer, full load iron loss of the transformer. Then we can find out efficiency of transformer at any load even without subject to that particular load. Now, considering the equation for efficiency, we know in case of transformer that the supply voltage remains constant. If we consider the power factor of the load is constant, then V2 is constant, cos phi 2 is constant, then Pi is constant. The only variable component is I2 and PC, because we know PC is equal to I2 square R equivalent. Now, if I2 is the variable quantity, now differentiating this efficiency with respect to I2, then we can find out the condition for maximum, so that the denominator will become minimum. For the minimum value of this denominator, we have to take first derivative of this component with respect to variable, and variable here is the secondary current I2. Taking the first derivative and putting equals to 0, the condition will come, that is Pi is equal to I2 square R equivalent, means iron loss must equal to copper loss, or constant loss must equal to variable loss. Now, in that case, we know the copper loss in a transformer winding is always given by I square, I square R, where I is the secondary current, whereas R is the equivalent resistance of the both windings. Then it will be I square R equivalent. Now, if we know the transformer efficiency will be maximum when this iron loss is equal to the copper loss, but at when transformer is subjected to any other load, but it doesn't mean that the transformer efficiency will be always at its full load. Let's consider the efficiency has occurred at a fraction of load, that fraction is x. Therefore, because load is described with the magnitude of current, then it will become x square, and into my I square R equivalent is equal to Pi, or simply x square Pc is equal to Pi. Therefore, this equation can be represented as x square Pc when we want to find out the loss of the transformer at any fraction of load x, and x here means that is full load value of full load P2 upon present load upon P2, the total load maximum full load capacity. The P2 is output. Here it is output. Output may be half of the P2. Output may be your one third of the P2, and hence similarly we can find out the fraction of load. It depends. Therefore, copper loss will change from if x is equal to 1 by 2, then copper loss will become 1 by 4. If x is equal to 1 by 3, then copper loss will become 1 by 9. Therefore, we can say in a generalized way, at maximum efficiency, the copper loss must equals to iron loss, but we don't know the copper loss is at full load or at any other some load. Therefore, this fraction is taken in generalized. Then x square Pc must equal to Pi. If this loss is if this condition occurs at full load, then x will be equals to 1. If this condition occurs at some any other load, then accordingly this fraction will be taken, and hence we can say the load at which the maximum efficiency may occur, it is given by Pi upon Pc under root. Here x is the fraction of load at which maximum efficiency can be achieved, and therefore the load at the maximum efficiency, if the maximum load of the transformer is given by kVA max, then the load at which maximum efficiency occurs is rated value into that fraction is x, and this fraction is obtained by having Pi upon Pc ratio and then under root. The significance of this fraction of load is more important when we want to calculate the efficiency of transformer at any other load than the rated value without actually changing the load. In case power factor of this load is not defined, then by default this power factor is taken as unity. Otherwise, the power factor of the load will be taken according to the given value.